This video is on scatter diagrams and correlation. Scatter diagrams or scatter plot diagrams is a graph that shows the relationship between two quantitative variables measured on the same individual. So here's just a general example of how a scatter plot or scatter diagram will look. Each individual in the data set is represented by a point in the scatter diagram. The two quantitative variables are the response variable and the explanatory variables. The response variable is the variable whose value can be explained by the value of the explanatory variable. So here we have the differences between the two in comparison. The explanatory variable is your predictor variable, your independent variable, normally associated with your x variable, and it would be on your horizontal axis. The response variable is predicted, it's dependent, it's normally associated with the y variable, and it is on your vertical axis. Here's an example of trying to distinguish between the two. It is hard to measure the height of people who are bedridden. However, it is not so difficult to measure the length of the ulna, that is the bone that runs from the elbow to the wrist. Data collected on non-bedridden people show a strong linear association between ulnar length and height, which variable should be plotted on the x-axis, which is explanatory, and the y-axis, which is your response. If we were to predict the height from ulnar length using the scatter diagram. So don't forget the prediction, the one that needs to be predicted will always be a response variable, and that is the key word in here, predicting the height. So that would automatically let us know that the response variable would be the height, and that makes our explanatory variable be the ulnar length. And also, if you look at the relationship, we're using the ulnar length to explain or predict our height. So that's going to give us credence on what our height would be, the ulnar length. Linear relation, when you have a scatter plot diagram that is best summarized by a line, then you have a linear relation. So the first two is just a general example of how your scatter plot can be best summarized by a line. We see one rising, the other one falling, but a line best summarized that. In the second one, a third one, excuse me, we have a non-linear relationship, which is the arc. And in the next one, we have like a wave. We still have a relationship there, a pattern, but they're non-linear. And then in the last one, we have no relation at all. Associations and trends. Associations or trends, they're the same thing. Positive associations or positive trends occur when one variable increases, the other one increases as well. So in other words, if you follow your graph from left to right, your graph or your pattern should rise. Notice from left to right, this goes up. Negative associations occur when one variable increases, the other one decreases. So following your pattern from left to right, it goes down or falls. Correlation coefficient is a measure of strength and direction of the linear relation between two quantitative variables. Population correlation coefficient will be represented by Greek letter rho. Kind of looks like a P, but it's actually Greek letter rho. That's your population correlation coefficient. The sample correlation coefficient, which is the one that we will be using the most, is lowercase r. Properties of the linear correlation coefficient. First one, it is always between -1 and +1 inclusive. If r is equal to +1, then a perfect positive linear relation exists. If r is equal to -1, then a perfect negative linear relation exists. The closer r is to +1, the stronger the evidence of a positive association between the two variables. The closer r is to -1, the stronger the evidence of a negative association between the two variables. If r is close to 0, then little to no evidence exists of a linear relation between two variables. Now, this does not mean, or this does not imply no relation. It just means that there is no linear relation. Remember, we saw previous example how you can have a pattern that's not linear. So r would be close to 0 in that case. Number 7, it is a unitless measure of association. And then number 8, it is not resistant. So in other words, it is affected by outliers or values that do not follow the overall pattern of data. So down here we have just general examples as to how your scatter plot diagram would respond. and how it would look if r was equal to certain value. So if r is equal to +1, then you would have a positive linear association, a perfect one, in which you have a straight line. And as you get closer to 0, the more you begin to deviate away from that line, and your data will start to spread, as we see in 0.9 and 0.4. R equal to -1, you have that same perfect line, but it will be going down. And as you go and get closer to 0, once again, your data will start to spread, your points will begin to spread. No linear relation, or R being close to 0, you can have that arc, as we discussed before, or just no pattern at all means that R is equal or close to 0. Here in this example, we want to determine the linear correlation coefficient between the club head speed and distance. So you're talking about swinging a golf club and how fast you swing the golf club. If you swing it at 100 miles per hour, in this case, it was recorded at 257 yards is how far the ball traveled. Here, the person swung at 102 miles per hour, and the ball went 264 yards, and so on. So this book does not focus on the calculation of the correlation coefficient or how well you know how to use the formula. They just focus on the application. So find an application, website, calculator, or something of that nature that will be able to calculate the correlation coefficient for you reliably. Easycalculation.com is one, but there are plenty of them out there, plenty of websites, plenty of free things that will calculate the correlation coefficient for you, and they are reliable. But once you do so, if you were to use these values, you should get 0.9387. And this suggests that there is a strong positive association. Okay, so that suggested that there was a strong positive association, but what we want to ultimately know as well is there a linear relation? So testing for a linear relation, the first thing you would do is determine the absolute value of the correlation coefficient. Whenever you take the absolute value of a number, remember it's always the positive result. So if you had the absolute value of 5, the absolute value of 5 is +5, the absolute value of -5 is also +5. So taking the absolute value of a number always yields the positive result. So you want to determine the absolute value of the correlation coefficient. Then find the critical value in table 2 from appendix A for the given sample size. We'll look at that in a second. If the absolute value of the correlation coefficient is greater than the critical value, the linear relation exists. Otherwise, no linear relation exists. So determine whether a linear relation exists between the club head speed and the distance. So we already calculated correlation coefficient to be 0.9387. Take the absolute value of that, it's still going to be 0.9387. It really matters when you have a negative value, they want the positive value. So no matter what correlation coefficient you have, they want the positive representation of that number. So now we'll go to the critical, go get the critical value from table 2. So our sample size is 8. If you go back to our data values, we have 1, 2, 3, 4, 5, 6, 7, 8 observations. So now we go to that chart, which is right here. When n, our sample size is equal to 8, our critical value is 0.707. 0.707. So we have 0.707 as our critical value. Now we compare the absolute value of our correlation coefficient to our critical value. Our absolute value of our correlation coefficient is greater than our critical value. So going back to step 3, if the absolute value of the correlation coefficient is greater than the critical value, a linear relation exists. So there is a linear relation that exists between the club head speed and the distance, and it is positive as well, going back to the previous example. So there is a strong positive linear relation between the two variables. All right. So let me know if you have any questions on what was done in any of this stuff.